Okay, all right, great. Welcome back. Today we'll sort of continue our discussions, but switch a little bit more towards quantum computing. So next two or three lectures, I'll try to cover some quantum computing topics and give more introduction to things like quantum computer programming to kind of get a better idea of how the systems work, and then we'll kind of go back and talk about more of the security topics. So to begin with, I thought to go over some brief history of quantum computing. I just maybe for fun to kind of give a little bit of background of different developments in algorithms or in hardware that has been happening over the decades, but also some of the roadmaps that are coming up from the uh, different companies. So quantum computing actually has a pretty long history. Some of the physics started, in the 1920s, and really a lot of work on quantum computing actually has been done more on the theory, on quantum mechanics, on quantum algorithms, really before there were any sort of practical realizations of quantum computers. So actually the history of for example, quantum algorithms, it's older than the history of the physical realizations of quantum computers. And really, I guess I found this nice timeline online. I think some interesting dates are sort of in the 80s. There was work on the Hamiltonian simulation and sort of looking at how do you simulate or proposing that you can simulate different systems using quantum computers. 1990s had a lot of, I guess, activity with different algorithms with like Shor's and Grover's and Deutsch-Jozsa and other type of algorithms that people were developing. In 2000, 2010s, things have kind of switched more towards things like now everybody wants to look at quantum machine learning, but also like variational algorithms that are used for optimizations on this computer. So there's long history and too many dates, but some interesting and maybe time points in quantum computing. So in 1980s, 1981. Richard Feynman proposed the concept of using quantum mechanical systems to simulate other quantum mechanical systems. So it's basically the idea of using a quantum computer to simulate another quantum mechanical system, like chemical molecules, for example. So really, it's 1980s. Then David Deutsch of the Deutsch-Jozsa algorithm in mid-80s proposed the concept of a universal quantum computer. And then basically demonstrating that a quantum system could simulate physical processes. Then in mid-1990s, Peter Shor developed the Shor's algorithm. So I guess this is always a strong motivator for quantum computers or work on quantum computers if you can actually have a big enough quantum computer to break cryptography by running Shor's algorithm. It does require logical qubits and error-corrected machines, but still is kind of one of, I guess, the most famous algorithms that is really driving the development of quantum computers. And then things like in 1995, Benjamin Schumacher proposed the concept of a quantum bit that we'll talk about quite a bit today. And then in another, Love Grover, Grover's algorithm provided the algorithm for the quadratic speedup on the search for on unsorted databases. So for security, we always think about the Shor's algorithm as the one that is being able to break public key cryptography, and Grover's algorithm that can help speed up search for cryptographic keys. So it cannot break, for example, hash algorithms, but or symmetric key algorithms, but you do have to double the size of the hash, for example, to prevent Grover's algorithm. So there's a lot of work, a lot of history on algorithms. Now, for the implementations, I believe really the first kind of working quantum computer was a 2-qubit machine in late 1990s. I probably quite famously in mid 2010s, D-Wave made available their quantum annealing machine, and for us, 2016 is when IBM made one of their machines available online for public use. So really, the cloud-based quantum computing paradigm, took off in 2016. And then, different kind of looking at the different implementations. So we had like the first demonstration of basic quantum gates in these nuclear magnetic resonance technologies in 1990s. Then the machine was used in late 1990s to actually run the Deutsch-Jozsa algorithm. And then then you had a 5-qubit machine from IBM. So in early 2000s, you had like less than less than five qubits, and different developments continued. For example, in 2004, the first use of trapped ions to implement 2-qubit gates. So now we have not just an NMR type of quantum computers, but also trapped ion machines. In late 2000, we had cluster state quantum computing. So these are photonic machines. So now we're adding a photonic based quantum computing, and then in late 2000s, 2009, the first superconducting qubit machine. So by I think by 2010, sort of there were demonstrations of all these major technologies from superconducting, photonic, and other ones. And then, yeah, 2010, 11, there was a D-Wave. I guess D-Wave's always somehow controversial because they keep their machines. I think sort of one of the main companies that sort of keeps their machines pretty secret in terms of the way they operate. So there's always some controversy. But D-Wave is not really a full-blown quantum computer. It's called an annealing machine. So basically, you can use it for optimization, but not like a general purpose quantum computing. And then from there on, you have different improvements in the fidelities of 2-qubit gates. So as we'll learn later, all the really computation quantum computers either uses single qubit or 2-qubit gates, and you need 2-qubit gates for entanglement. So everybody keeps trying to make better machines, and one of the things that people are improving is the fidelities of the 2-qubit gates. And then then we have a 10-qubit machine, and then some demonstrations from Google and others about quantum supremacy, showing that certain algorithms can be computed on the quantum computer that couldn't be done classically. And yeah, we already mentioned 2016, we had the IBM Quantum Experience with their machines online. So this is really when kind of quantum computers became accessible to people broadly through the internet. And again, continued advancements in the different machines. Now we're into like 200 physical qubits from superconducting machines in 2021. And more work coming up on sort of demonstrating quantum error correction. And really by 2023, 24, pretty much all the companies have sort of switched to works on fault tolerant architecture. So so last year we missed it, but last year was the International Year of Quantum Science and Technology to mark 100 years of quantum mechanics and sort of all the quantum related things. So a lot of advancements, and we'll see what what happens this year. So this was sort of the history of some of the developments in quantum computing. Before jumping into the quantum computing concepts themselves, I thought to show some of the roadmaps from the different companies to give you an idea where the technology is going and what at least what the companies are really focusing on. And this is sort of a random selection from some of the major companies. I missed some companies, so just a random selection of nice roadmaps from the different vendors. And for example, IBM has been putting out these roadmaps for quite a while, and you can't really see it, but basically we're into 2025, and I know we're in hundreds, 200, 300 qubits, and then the goal for IBM at least is now we have error mitigation, and you switch to fault tolerant by the end of the decade. So we go from few hundred to maybe thousands of physical gates, and then that enables you to have 200 or 2000 logical gates. So the aim is to have logical qubits by the end of the decade, and in hundreds or more of them. And then I don't think this roadmap shows it in detail, but for example, of course, IBM is working on technologies like chiplets. How do you really build these bigger quantum computers from individual components? IQM is a different superconducting company, but similar roadmaps that we're in 2025 with number of qubits in the low hundreds, and then really by But again, by 2030, really switching to logical qubits and having on the order of hundreds of logical qubits. So uh, yeah, similar from Rigetti, another superconducting vendor, where again by the end of the this decade, they want to have support logical gates and have very thousands of physical qubits that can be used to actually implement those logical qubits. This is from IonQ. Is the most ambitious in terms of having a few thousand of logical qubits by the end of the decade. So this is their goal for, and again, you can see the similar ratio of tens of thousands or hundreds of thousands physical qubits, and those can be used to realize hundreds or thousands of logical qubits. And both IonQ and actually Quantinuum are trapped ion machines. So it's a different technology from superconducting machines, but likewise, Quantinuum has plans for thousands of physical qubits that translate to hundreds of logical qubits. So it's kind of the ambition for the companies. And another one, QEra, which is a sort of an analog type quantum computer, but they're also aiming for the equivalent of having tens of thousands of physical qubits going to logical qubits. And again, and that's just another example. Pascal, one of the companies that actually now has an office in Chicago, recently opened. So again, they're aiming for having 200 or so logical qubits in 2029. So I think maybe the takeaway from all of this is that a lot of the technologies have already been established, like superconducting machines, and now people are really shifting to how do you design logical qubits, and there is some sort of a consensus of having a thousand or 2,000 or 3,000 of logical qubits by the end of the decade, which actually sort of corresponds with the recommendation of people to transition to post-quantum cryptography by the end of the decade. So it's kind of things are converging, but a lot of the companies are also working on chiplets and different ways to actually build these such big quantum computers. I mean, you cannot fit 100,000 qubits in one fridge. So there's a lot of technologies that need to be deployed, and a lot of integration with sort of high performance computing, or putting the quantum computers inside the data centers. Yeah, so this is kind of the some a little bit of history and roadmaps for the quantum computing technologies, and maybe now I kind of want to switch a little bit to introduce different quantum computing concepts, and just kind of introduce them in high level today, and then we'll talk more about quantum computing programming in the next meetings. But kind of maybe to begin with, so what's a quantum computer? Well, what's a classical computer? So classical computer basically leverages voltages and currents flowing through different circuits to realize logical gates and or XOR, and then from those logical gates through Boolean algebra, you can kind of create any type of computation. So you're using physical quantities such as voltages or currents to really perform computation. On the other hand, in a quantum computer, we're trying to leverage quantum mechanics and principles of quantum mechanics to perform the computation. And sort of the key features, I think, of quantum computing is the superposition, entanglement, and interference that we'll talk about it. So these are properties of qubits that can be leveraged to basically represent large amount of information in the qubits, and then through things like entanglement, you can correlate the behavior of the qubits, and then interference actually allows you to do some useful computation on those entangled qubits which are in superposition. And then, so a quantum computer is basically a device that has these qubits. There can be superconducting, photonic, or other types of qubits, and then each qubit sort of represents the information that you then transform by applying different gates, which transform the state of the qubits through the properties of quantum mechanics. Just as an aside, there's sort of uh, I guess three types. Well, but there are probably more, but there are different types of quantum computation, and there's mainly analog based quantum computers, digital based quantum computers, and measurement by based quantum computing. So these are different ways of performing computation, and the analog, sort of like the name implies, is basically you have some quantum information, some quantum states, and you sort of slowly evolve them following some rules to try to achieve the solution. So like quantum annealing with D-Wave, for example, is one example where you have a analog computer where you sort of evolve the state from some initial state, typically to like a lowest energy state, which corresponds to the solution to your problem. And then you have digital quantum computers where basically you try to, the way the quantum states are evolved is broken down into these quantum gates or digital or individual steps. So the quantum computation is sort of not like done smoothly, but at each time you apply a quantum gate and you transform the state step by step. So it's like a digital, I guess. And then at the end, again, you just measure and get the results. And so here, majority of the machines like Rigetti, IQM, IBM, all these are mainly digital quantum computers. And then there's also some exotic things like measurement-based quantum computers, which I don't know very much about, but basically the key idea here is that you, instead of evolving the state, for example, a set of gates, you prepare the states in a highly entangled state, and then from that you can perform computation. So, for example, PsiQuantum, which is one of the companies coming to Chicago, building a large factory on the south side of Chicago, is that type of a quantum computer. So there are many different means of achieving quantum computation, and in this class we'll really focus on the digital quantum computers by and then how they apply gates to the quantum states to achieve the computation. Here. Before diving into that, maybe another aside, a little bit different picture, but also showing how the typical quantum computer system is built, where we'll talk about the qubits, where the actual computation is performed, but the qubits again are interacting with some controller, which tells it how to execute the quantum gate. So when we talk about the quantum gates, there has to be something that tells the system when to execute those gates. So this is the controller. It reads out the information, and then this forms the quantum processing unit, and then the operation of the quantum processing unit is sort of managed by a classical system that, for example, might be optimizing some parameters of the gates and again executing them on the QPU. And I think one important again, another side, an important thing is that really quantum computer is even a sort of a universal quantum computer is still going to be more like an accelerator. So you can think of a quantum computer like a GPU that can run some algorithms like Shor's very efficiently, but it will never really be like a complete standalone a computer. It's always going to be some sort of an accelerator. And so you need some classical computers for doing pre-processing of the circuits, executing the circuits, and then maybe post-processing the data. So really, when we think about quantum computers, even when we talk about universal quantum computers, it's more about like an accelerator that's good at running few algorithms, and then there's always a classical computer that manages it and kind of interfaces with it. So that's just another aside. And okay, another aside. When we think about quantum computer, it's also quite simpler than today's computers, but it's very much like early computers from a few decades ago. So first, when the classical computers were built, you would have some devices, maybe even vacuum tubes, and then you basically directly program the logic gates and you implement the algorithms by sort of we call now bare metal code. You just directly run on on the logic gates. And then over the years, we have, like now we have algorithms that are programmed in some higher level languages. Then you have compiler, operating system. There's many layers in the computer system. But if we look at the quantum computer, it's really it's really like a very early classical computer where again there's no operating system. There's really just sort of algorithms that get compiled to circuits that execute on these devices. So like the complexity, at least for now, is on one hand they're of course very complex. On the other hand, it's just really algorithms running directly on these qubits. Um, so um, so it's simpler, but but still has many components, noise mitigation, error correction, things like that. It's quite many things going on. Okay, but at the bottom are the qubits. So I want to kind of give just a very, very brief introduction to some ideas of quantum mechanics and wave functions and things like that kind of help understand how eventually the computation is done on the quantum computer. So really the basic is for all of this is quantum mechanics, basically describes how microscopic particles like photons or electrons behave and how their states evolve over time. And you can compare classical mechanics to quantum mechanics. That in classical mechanics you have Maxwell's equations, Newton's laws, and sort of everything evolves according to those laws. And then things like energy can be is continuous, and most importantly, if you can fully determine the state of the system based on the information such as the position and velocity of the particles. So you can really determine the state exactly of the system. And on the other hand, we have quantum mechanics, which focus more on atoms, electrons, photons, on microscopic particles, and then we get into the Schrödinger equations that kind of predict how these particles evolve, how their state evolves over time, and most importantly, now at the quantum level, energy is quantized, so things are no longer continuous. And then we also have the Heisenberg's uncertainty principle that you cannot precisely know all the parameters of the system. So we're sort of and then so the quantum computing is sort of trying to leverage these properties to build some useful ways of computing. So in quantum computing, we have the qubits, which really represent the quantum states, and the quantum states are represented by this. Maybe you've seen the ket notation. So the psi is the quantum state inside the bracket, and then that's the quantum state. That's the information of the system, and then over time you can use Schrödinger's equations to see how the state changes. So basically, if you have the psi is the state, and psi xt is also called the wave function. So again, it represents all the information about the quantum state, and then it evolves over time according to some Hamiltonian operator h. So this is the kind of the Schrödinger's equation, and you have the how change, so how the wave function changes over time depends on this Hamiltonian. And then so the Schrödinger equation is sort of this fundamental equation in quantum mechanics, and it really determines how the state of the particle changes over time. So you apply the Hamiltonian to the state to go to the next state, and then later on, that's how we'll actually achieve some useful computation. It's similar to Newton's laws, but it doesn't predict the position and velocities. It sort of gives us the wave functions, which then can be used to determine the probabilities of the particles. And then so the Schrödinger's equation really introduced the idea that you have these particles like electrons, that they behave like wave functions, and then if you have a wave function, you can take the square of the wave function to find the probability to get the probability of getting a particle in certain positions. So this is when you do a measurement, you effectively collapse the particles and then find out sort of where they are, but you lose all the quantum state. So the quantum state is really uh, inside the wave function. Yeah. So and then one implication of the Schrödinger's equation is that basically that um, excuse me, that the implication of the equation is that as the time changes, sort of your system evolves according to these what are called unitary transformations. So you often see this U operator. So basically, sort of says how how the state of the particle changes over time, and then this unitary encodes that. Um, and then in some, is a direct correlation to the Hamiltonian. So basically, from the Hamiltonian, you can find these unitary operators that determine how the particle behaves. And very very interesting property of the quantum computation is that these unitary transformations are reversible. So basically, any quantum computation that you can do, you can always reverse. And then ideally, if there's no interaction with the external world or with the external system, there's no energy loss when you're doing the computation, and that's why you can reverse it. So all the so the system is perfectly isolated from the environment. All the unitary transformations, all the computation is reversible, and it doesn't, and there's no energy loss in that process. So it's a yeah, so you can very quickly you can run some computation forward, and then you can run it backwards if you wish in the other direction, and all the information remains within the wave functions until you perform a measurement. Um, um, so that, yeah, so you have this wave function that represents the quantum state or the qubit, and maybe you've seen this equation also quite often. So in general, a state of the qubit can also be represented as a combination of these two basis states. So you can think of it that in like a in a realization of a quantum computer or a quantum computing system, you have either, let's say, like a low energy state and a higher energy state, and then basically the state of the particle is some combination of those two, which is specified by these alpha and beta, which are the complex amplitudes of these basis states. And I think we've mentioned before that the square of the amplitudes gives you the probability of finding the state in the qubit in a specific state. So in a two-state quantum mechanical system, this is either 0 or 1. So you can get the probability if the qubit ends up in a 0 state or 1 state based on the probabilities which come from the wave functions. And then there's some restrictions that the complex probabilities fit this equation where ace alpha squared and beta squared ends up being 1. Which brings us to another thing that you've probably seen a little bit, is that this block sphere, which is basically a way to visualize a state of one qubit of one quantum particle. It cannot be extended easily to multiple qubits because you get more dimensions, and I don't think we know how to draw it, but at least for a single qubit, basically it represents the state of the qubit, and because alpha and beta alpha squared and beta squared equal 1, you get this unit sphere where basically you can think of the state of the particle is some point on that sphere, and yeah, so it's on that sphere, unless it's a mixed state. So if the particle somehow is prepared not ideally, or maybe it's interacting with the environment, it wouldn't be on the sphere, it would be somewhere in the sphere. But for a pure state, it's on the sphere. And then one thing that's useful to know, that basically when you do the measurement, basically you're trying to figure out where the particle is, and then you can do measurement across any of the axes, but typically the measurement is done with respect to the z-axis. So basically, uh, if you're in the zero state, then sort of your particle will be on the top of the sphere, representing the zero that you measure. And if it's on the bottom of the sphere, then it will be one. Then you got one that you measure. And then during the computation, it will be sort of anywhere you wish on the sphere, and then sort of it's collapsed to either a zero or a one. But the key part is that this is only for, it's a nice visualization, but it's only really for one particle. And because it's a sphere, you could also represent the state as with respect to the angles to the axis if you want it. Yeah. So in the end, we have a qubit, which is basically this fundamental unit of information. That sort of represents the wave function represents all the properties of the qubit, and generally it's a superposition of these two basis states, either zero and a one. And unlike classical bits, the qubit can be sort of in 0, 1, or any superposition of those. That's where you get the idea of having many states that can be, 2 to the n states can be represented by just n qubits. So I think we had this aside before, but you have qubits that are made of sort of two basis states. You could have qubits that are made of three three basis states, or even q modes that are made of more basis states. So there are other ways to build qubits or q modes, but we really focus most of the work here just on the qubits and how do you work with qubits. And I also showed this very briefly before, but each qubit has to be realized in some sort of a physical particle, so a photon and an electron, or like a superconducting junction. So when we talk about the qubits, they all follow the same laws, but they can be realized in different ways. And they're mainly sort of manufactured qubits, where you create a qubit out of like a superconducting junction, or sort of, let's say, natural qubits, where you use like a ion, like just a particle or a photon, where it's really a natural particle that you realize for the qubit. So there are many different ways of realizing them, but in the end, again, for the classical bits, you have either 1 or a 0. It can be measured completely. When you measure 1 and 0, typically is not changed by the measurement. You can copy the classical bits, or you can erase them, you can zero them out. For qubits, we have the superposition, and then when the key part is that basically when you measure the qubits, again, the wave function collapses and you get 1 or a 0 out of it, but you lose the quantum state, so it's changed by the measurement. And so the measurement is, for example, not a unitary operation. So all the different quantum gates we'll talk about are unitary operations that can be reversed, that can be used to evolve the wave function, but a measurement is not a unitary operation, because once you measure it, it collapses the state, so then you cannot sort of undo the measurement to get back into the quantum state you were before. And also the qubits cannot be copied. There's a no cloning theorem that you basically cannot copy, because you cannot perfectly measure the quantum information. You cannot perfectly copy it, so you cannot copy things quite easily. And then it's there's really no way of again, since everything is reversible, there's no really way to erase it unless you measure it, or unless you wait for decoherence. So decoherence happens when in a physical realization of the qubit, that the qubit interacts with the environment, and over time it basically loses its state and interacts with the environment, loses its state, and eventually, let's say, loses the energy and becomes all zero, which is equivalent of erasing it. So yeah, if you use unitary operations, you cannot really erase things, but you can, through decoherence, for example, or measurement, you can erase the qubits. Uh, any questions? I don't know, a lot of different things. Uh, okay. And we mentioned some of these properties like superposition and entanglement. So and interference. So I think these are the three main things. Remember, the superposition, entanglement, and interference. And effectively, the superposition basically means that the particle can be in any combination of the basis states, not just one and zero. So allows you to sort of represent lots of data with few qubits. So you can think of like a huge parallelism. You can have exponentially large state space, where again, with, for n qubits, you have 2 to the n different possible states, and then this really allows you to represent a lot of data, but by itself, it's not really sufficient to get useful quantum computation. Really, to get useful quantum computation, you have to combine this with interference, because this is sort of means that you can represent a lot of things in parallel, but then somehow you actually have to, reduce, the different states to the useful state. That's the solution of your computation. And sort of as an aside, again, we have this, maybe probably you've seen the Schrödinger's cat, sort of the idea that, when we have a particle, it's in a superposition of different states, and we don't actually know which one it is until we actually measure it. So in the experiment, or in the thought experiment, there's the idea of having this cat in a box, and you don't know if it's alive or dead until you actually open the box. And it's sort of kind of tries to represent that the fact that the qubit can be in a superposition of different states, and especially if you have such a 1 over square root of 2 for the different amplitudes, and the probability becomes 1/2 for each of the states. So as long as the particle sort of exists in the quantum space, you don't know which one it is, and then only when you measure it, it collapses to one of the states with probability. And of course, if it's exactly 1/2, then it's sort of 50-50 getting one state or the other. But in real quantum computations, some of the states would have higher probability. So that's basically the goal of all the quantum computation is you take some qubits which are in superposition, you entangle them, and then you apply interference to increase the probability of certain states, which are the solution to your computation, and then somehow decrease the probability of states that don't correspond to your computation. So that by the time you finish your computation, it's not that all the states have 50-50 probability, but there's one state or some pattern of states that have higher probability, which correspond to the solution of your computation, which brings in this idea of the interference, is that interference is a fundamental property of quantum mechanics, and basically, since these qubits are effectively represented as waveforms, the waveforms can interfere with each other. So that means you can have actually kind of like in ocean waves, you can have constructive or destructive interference. Things can add up together, or things can cancel out. So basically, quantum amplitudes, you can be cancel each other out or reinforce each other. And then so really I think this is really the key part of all the quantum computation that maybe sometimes we pay less attention to, that really when you design a quantum algorithm, basically you have to, or you try to exploit this property and you engineer the circuit such that the amplitudes along let's say the incorrect computation paths diminish, they cancel each other out, while those along the correct paths accumulate, basically making sure that a state that corresponds to your solution has the highest amplitude. So when it's measured, that's the output. So I think a lot of times we focus on like superposition being like the key property of quantum computing, but I think it's really the interference. Like without the interference, you just have bunch of states represented by the qubits, and no easy way of figuring out which one is the correct state or not. So the more, so any sort of any practical or any useful quantum algorithm has to perform interference to really amplify the states that correspond to your solution. And the magic of writing quantum algorithms is exactly, how do you engineer the circuits to amplify certain states and diminish the other ones. That's kind of the I would say I don't know, the art or the magic of quantum algorithm design is uh, where and how to use interference to drive the qubits away from some states and towards the ones that you want them to be in. So if yeah, so remember this, superposition, but interference equally important, maybe even more so to actually achieve if your algorithm isn't using interference, it's probably not getting any quantum advantage at all in the computation. And then another the third property is the entanglement, which basically means that you correlate the behavior of two or more particles. So um, if you have a bunch of qubits that are sort of individual, then you're not really gaining any benefit. It's when you entangle them, then the behavior of one qubit becomes correlated to the other qubit, and then you can build a bigger. So then you can have a entanglement allows you to have a system built of many qubits, and then you can perform computation on those qubits. And there's the sort of the this very cool, experiment and a kind of demonstration of the entanglement, where sort of when you entangle two particles together, their behavior becomes correlated. So let's say if you entangle, two particles, maybe their spin is always up or always down, and then this actually the spooky. I think the quote is like, spooky action at the distance is like, if you entangle two particles and then you send them very far apart, they're still entangled regardless of the distance. And it's kind of demonstrated experimentally. It's hard to explain. One thing about that, the sort of the entanglement though, is that while the particles remain correlated, this doesn't break any sort of laws about, like speed of light and how far you can transmit the information. And that is because even though the particles are correlated, to observe that, you have to measure them at the same time. And then so to measure them at the same time, even if they're sort of infinitely apart, you have to have a signal that's sent to both particles to measure them. And then that signal that's sent to the both particles to measure them is limited by the speed of light. So, yes, the particles are infinitely far apart, but you cannot actually measure them simultaneously unless there's like this measurement signal that's sent across them. So they're entangled. They somehow, through the quantum mechanical properties, they're always working together, but it doesn't break things like, speed of light, and that you cannot transmit information faster than speed of light. But the key part is, entanglement to get the particles together, and then, interfere them to highlight one of the states that corresponds to the solution. And I think that the key part is how do you actually design the algorithms to have this interference. So very briefly, to get into sort of how do you actually transform how do you change the states of the qubits. So basically, in quantum computing, we apply quantum gates to change to basically evolve the state of the qubits or the waveforms. And you can sort of think maybe that each quantum gate sort of corresponds to like a Hamiltonian that determines how the state of the qubit should be changing. And there are various standard gates that we'll cover next time, such as Hadamard gate, Pauli gates, CNOT gates, and they all are represented by these unitaries, that means that you can basically they're all reversible. And then I think I showed this a few lectures ago. The way you apply the gates is you start with some quantum state psi, you apply the unitary to get to the next state, and then you keep repeating that. And so in the digital quantum computer, I guess the reason it's digital is that there's a integral integer number of steps where you apply a unitary, you go to the next state, you apply a unitary, you go to the next state. You kind of keep doing it step by step, and that's how you perform the computation. And again, yes, so sort of just remember that the quantum gate is a sort of a unitary operator that's acting on the state of the qubit. It can be acting actually on more than one qubit. Typically, we have, as we will see, we have either single qubit gates where you modify the state of of a single gate, sorry, and two qubit gates where you apply the modify the state of two qubits, and you need at least one 2-qubit gate to achieve entanglement. So sort of the simplest set of quantum gates is a number of single qubit gates and one 2-qubit gate to enable you entanglement among the qubits. But since the gates represent unitary operations, these unitaries are actually not limited to one or two gates. You could have many. You could operate on many sort of qubits. You can transfer them together, but realizing in practice, realizing more than 2-qubit gates seems very challenging. So most of the quantum computation we'll see is just 1 or 2-qubit gates that are used. And then so we've already kind of seen a preview of this picture that you have these the circuit is effectively described by showing how you have a set of qubits that are modified by the different gates, so the different unitaries that are applied to them, and then so you have the initial quantum state, and then you apply all the gates, then you do the measurement. Sorry. If you get the measurement, then you collapse the final state to some value. But if you wouldn't do the measurement, you would end up in a different state, and that's how the circuit works. And in a perfect world, everything is reversible, and you could have even bigger gates that would work on many qubits. But in practical quantum computers, we only have either 1 or 2-qubit gates, and then all of these gates actually introduce some error. So also, when we think about the computation as applying unitary gates, this can be done forever. You could keep evolving the quantum state forever, but in practice, the realization of these quantum gates is not perfect, and we have things like decoherence, for example, or gate noise, where after a while, effectively you lose the state of the circuit. So in practice, the gates are not perfect realization of the unitaries, and there's only a limited number of gates that you can apply before so you lose or mess up the quantum state. So that's some practical issues that people are trying to solve by having better gate times, but also by having error correction to detect when and correct when errors are happening. And then finally, we have at the end of the circuit, we have these measurements. So when you evolve the state of the qubits, you end up with some wave function. But you want to get some answer out of the circuit, you actually want to do the measurement, and then sort of when you do the measurement, you effectively, based on the amplitudes, things get collapsed to some output state, and then if it's a single qubit, then you need alpha squared or beta squared. But similar idea applies to multiple qubits when you do do the measurement. And then again, the key part is sort of for all the algorithms to use interference such that by the time you get to sort of to the end where you're about to measure, there's only a one state or a subset of states that have high amplitudes that when you measure them, they'll give you a one and everything else will give you a zero. And then that's the solution of the algorithm. So again, if you don't have much interference um, in your um, in your algorithm, then you're probably not doing much quantum computation. Um, I think that's something kind of important to highlight. Um, okay, so yeah, yeah, and so maybe yeah, I already talked about the decoherence, right? So basically, just to more specifically, so decoherence is the sort of the process where you lose the superposition, maybe the qubits sort of interact with the environment, and they uh, lose some of their energy, and then basically once when the qubit decoheres, it's no longer able to maintain the superposition, and you effectively lose the quantum state and it just becomes a classical one or a zero. So decoherence is a big problem that sort of a engineering or problem for building practical quantum computers. How do you mitigate decoherence? And like, for example, for the superconducting qubits, you always put them like in a super cold fridge to isolate it from the environment to make sure it doesn't interact. So you have to make sure that these qubits are just interacting with each other and not the environment around it. Otherwise, you lose the information. Um, so preventing decoherence, I think one of the biggest challenges. There are many challenges in quantum computing, but this is a pretty large one. Okay, so okay, I guess maybe we're a little early today, but this is kind of what I wanted to talk about today. So hopefully gave a little bit of introduction to some of the history of quantum computing, some of the roadmaps to see where things are going, and then sort of introduce some basic quantum computing concepts. So next time we'll talk more about the quantum computing concepts, more specifically about the different quantum gates. How do you use them to achieve entanglement and some of the computation? And then after that, maybe the following meetings we can do some sort of programming examples of different circuits in actual, not just in pictures, but actual programs. So yeah, so I think this kind of wraps up kind of the introduction that I want to do today, and yeah, we'll continue next time.